friends forever. You know, even though I'm a ghost, blue sheep, I will always love you the most. Blue friend, blue will take the pain away. Blue sheep, so we can see the sun another day. Forget about the days of past. Blue sheep, our friendship is the one that will last. Blue friend, you know we can make it through, me and you. So give everyone a little bit of blue.
Under the moonlight, we fight side by side with scales and blades. Our hearts open wide in high rules embrace. No shadows to hide. Together with courage, we conquer the tide. Pink and silent in a world so wild. Two different souls, but our hearts reconcile. With every battle, our love compiled. In the depths of danger, our spirits smiled.
What's your name, sir?
My name's
You
Deez.
even wrote me into this! 'Cause he
Deez what,
wrote
sir?
me into
Deez
this!
Dog.
He wrote me into this! He wrote me into this!
Not telling the things you were laughing about me. I'm dead. Bet you never did.
Sir, let me see your ID.
Ah, shucks.
Ow, shucks. Hi everyone, how you doing? Long time no see. It's been a hot second. But we are here this evening testing out the streaming software one more time, making sure everything looks good. Because we got a busy October coming up. I don't know if you checked out the October stream schedule, but we're going to try to get back to at least 2 or 3 times per week until we get to Halloween week, where we will have a week-long Halloween special. Where we will be playing Look Outside. I've never played it before. I've seen some renditions of it on YouTube. It looks really good and a little spooky for spooky season, so I'm very excited for that. Alright, I'm gonna move the music down a little bit. We are starting right away. I want to see what does it... Does it do anything at 0? It doesn't... Oh, it doesn't do anything? Okay, fine. The plan today is just to make sure everything is set up, looking good. We're going to do a little bit of machine learning.
Here we go!
Hey, the wheel's working! Yay!
Advanced algorithms.
I need to make that wheel bigger.
No remainder.
Oh. That QED chance reminds me that I need to fix the bot. That one? Oh, that might be... No, that one shouldn't be too bad. Nice.
Problem solved.
By the way, how are y'all doing today? I have had a great Sunday. I was at work earlier today, so over at the brewery. It was a great day. Like, the sun was out. It was pretty warm outside. Everyone was coming in, having a beer on the patio. So yeah, just a really good day. I got a report done while I was doing schoolwork and brewery work at the same time. It was great. Hi, Lobster. How you doing? One more. Oh my gosh. You're at 68. Ah! You're so close. Just one more wheel spin. So I'm pretty good. I think I'm doing pretty good. I think things are looking great on all accounts, which is awesome. We're gonna do a little bit of machine learning tonight, so we're just gonna bust into a new chapter. It looks like chapter 5 of the Reese textbook. So if you do want to follow along, head over into the elements, and the machine learning channels are still in here. And if you want to grab some of the resources, they're all in here. I'm just kind of reading through Machine Learning with R in Tidyverse and MLR by Reese. So we're on chapter 5. I'm just going to keep on trucking through. We might have to break out some R today. Actually, let's get that set up just in case.
That final GPT%.
Ah, Show. Show is probably not alive yet. I'm sorry. I don't think I fixed Show yet. We could try to fix Show today, too. Yeah, that's what I wanted. All right.
Let me call you daddy, 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 daddy. Let me call you daddy, 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 daddy. Let me call you daddy, ooh, daddy, daddy.
Speaking of daddies, hello, Famished. How you doing? What was I doing here? Let's add a new script. And let's just get rid of all of this bullshit. See ya. That looks good. We probably do need to open up these similar libraries. All right, let's get them opened up. Just dealing with fatigue, oh no. You know what I did to help me deal with fatigue earlier? I had a Monster energy drink, and it was delicious. Disable until sunrise. There, now hopefully it won't be super orange for you. What Borg? What Borg are we releasing? Okay, I have no idea what this title even means. It says classifying by maximizing separation with discriminant analysis. I literally have no idea what that means. It was so, oh my gosh, it was so good, Famish. I'm gonna show you. It was the Monster Peaches. It was the best Monster energy drink I think I've had in my life. It was so good. It was like the peaches and cream. That's what it was. Peaches and cream. Highly recommend. It wasn't that like weird, like sometimes when you have like peach flavored things, it's kind of tastes like a little bit fake. But this one has a nice balance. It's like only a little bit fake, but like a lot of not fake. So I was very happy with it. Very happy. What all contributions to machine learning are steps taken towards releasing the Borg? Well, I mean, that's probably pretty accurate, actually. I do feel like all of us that are like teaching large language models are eventually literally just like creating our cage. We're just like, and we're doing it dirt cheap. What are we doing? Understanding linear and quadratic discriminant analysis. Building discriminant analysis classifiers to predict wines. Yes, I knew I wanted to do chapter 5 for some reason. Okay, discriminant analysis is an umbrella term for multiple algorithms. How's size for you guys? I can probably make this a little bit bigger if you want to read along. A little bedtime reading. Umbrella term for multiple algorithms that solve classification problems. Okay, so classification being we're going to input an unknown item into the algorithm, and the goal is to predict a specific variable or a specific feature. And I think classification usually is on either like a discrete numerical data, or it could be on categorical data. Right, so I think usually it's like a category, and we're trying to slot somebody into one of these categories. So So while there are various discriminant analysis algorithms that learn slightly differently, they all find a new representation of the original data that maximizes the separation between the classes. I have no idea what that means. Okay, the separation between the classes. That just sounds racist. It sounds classist, actually. It sounds a little classist to me. That might be the coffee. Oh yeah, the coffee crash. Yeah, coffee crash got me today, but the energy drink is keeping me vibing right now. So, recall from chapter 1 that the predictor variables are the variables we hope to contain the information needed to make the predictions on the new data. Right. So we're going to input a bunch of predictor variables, and we're hoping to our output is going to be one of these new features. Right. So discriminant function analysis algorithms find a new representation of the predictor variables, which must be continuous, okay, by combining them together into new variables that best discriminate the classes. Sounds a little discriminatory. Anyway, this combination of predictor variables often has the handy benefit of reducing the number of predictors to a much smaller number. Now, I could see that being super handy. That's really nice. Like, imagine you have a data set that has like 100 predictor variables. If this algorithm can look at those 100 variables and somehow narrow that down to like the 5 or 6 most important ones, I could see that being super valuable. Because of this, despite discriminant analysis algorithms being classification algorithms, they are similar to some of the dimension reduction algorithms we're going to do in part 4. Cool, that sounds really interesting. So they say dimension reduction is the process of learning how the information can be condensed into a smaller number of variables with as little information loss as possible. See, that's interesting. Because I feel like if you have a large number of variables and you're trying to condense all that information down, you're going to lose some information. But they're going to try to, I guess, minimize the information loss. That's kind of cool. So imagine that you want to find out if you can predict how patients will respond to a drug based on their gene expression. You measure the expression level of 1,000 genes. Are we talking gene gray or gene black? I'm just kidding. And record whether they respond positively, negatively, or not at all. So 3-class classification. A data set that has as many predictor variables as this. What? Oh, 1,000 genes. I see. I see. So we have 1,000 variables. And we have one classification of how they respond to the drug. Okay, I see. So it's actually 1,001 features. We're going to input 1,000 features. And the last feature is a 3-part classification. Okay, got it. So a data set that has this many predictor variables, 1,000, isn't rare. Yeah, I could certainly see in the topic of bioinformatics that could be. That's probably tame. The data is very difficult to explore and plot. Yeah, if it has 1,000 features, absolutely. There may be many predictor variables that contain no or very little predictive power or predictive information. Right. So this secondary bullet's probably really important, right? So if there are predictor variables that don't add a lot to what we want to work with, why are we using them at all? We could just trim that out. And then the other problem, they say we have the curse of dimensionality to contend with. What was this again? A problem algorithms encounter when trying to learn patterns in high-dimensional data. Curse of dimensionality. This sounds kind of like, this is very Halloween-y. Curse of dimensionality. So the common theme of these problems is that when the dimensionality increases, the volume of the space increases so fast that the available data becomes sparse. So in order to obtain a reliable result, the amount of data needed grows exponentially with dimensionality, right? And then organizing and searching is challenging. Yeah, okay. All right. So in our gene expression example, it would be nearly impossible to plot all 1,000 genes that we could interpret. Yeah, makes sense. So instead, we could use discriminant analysis to take all that information and condense it into a manageable number of discriminant functions, each of which is a combination of the original variables. Put another way, discriminant analysis takes the predictor variables as input and finds a new lower dimensional representation of those variables that maximizes the separation. I still don't know what that means. Therefore, while discriminant analysis is a classified... Okay, yeah, they said that already. Okay, let's see if we can figure out what the hell's going on here. Due to their dimensionality reduction, okay. So original data, we have 1,000 classes. Positive, negative, none. I see. So this is the output at the bottom here that we're looking at. So this says df1, df2. So discriminant analysis takes these classes, shrinks it down into dimension functions. Is that what they said? Discriminant functions. I assume that the discriminant functions must take as input the classes. Take the original data and combine continuous predictor variables together into new variables. Yep, so combine continuous predictor variables together into new variables, that's the df1 and df2, that maximize the separation of the classes. I still have no idea what that means. What does that mean? Why are we trying to separate the classes so much? So the number of discriminant functions will be the smaller of the number of classes minus 1, or the number of predictor variables. So in the example above, the number of classes is 3, positive, negative, none. So when they go to create the new dimension structure, we're going to get 2. Number of classes minus 1. Or the number of predictor variables. Okay, so if the number of predictor variables is already less than the number of classes minus 1, we don't really have to do anything. So in the gene expression example, the information contained in the 1,000 predictor variables would be condensed into 2 variables, 3 classes minus 1. Got it. We could now easily plot these 2 new variables against each other to see how separable the 3 classes are. Are these are all continuous? They're saying these are continuous variables, right? So if these are continuous variables, I guess we can plot it in the xy plane in this particular case. Okay. As you learned in Chapter 4, including predictor variables that contain little or no predictive value adds noise, yes, which can negatively impact how the learned model performs. When discriminant analysis algorithms learn their discriminant functions, greater weight or importance is given to predictors that better discriminate the classes. I see. So there's something about creating these new functions that's going to help the model better discriminate the classes. That's what they mean by separation of classes. Okay. Why don't they just call it discriminating the classes instead of separating the classes? Predictors that contain little or no predictive value are given less weight and contribute less. To a degree, this lower weighting of uninformative predictors mitigates their impact on the model. Despite mitigating, a discriminant analysis model will still tend to perform better after performing feature selection, removing weakly predictive predictors. Okay. So the curse of... I love this. The curse of dimensionality is a terrifying sounding phenomenon. Ba, 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 that causes problems when working on high-dimensional data. Yes, as the feature space increases, the data in that space becomes more sparse. Put more plainly, for the same number of cases you increase the feature space, the cases get further apart, and there's more empty space between them. Oh, I see. So if we're trying to do continuous kind of stuff, that's lots of calculations, right? And lots of potentially big calculations. The consequence of this increase in dimensionality is that the area of the feature space may have very few cases occupying it, so an algorithm is more likely to learn from exceptional cases. Oh, interesting in the data. When algorithms learn from exceptional cases, this results in models that are overfit and have a lot of variance. So for most random, adding predictors with valuable information improves the predictive accuracy until it does. What? Okay, what? Adding predictors with valuable information improves the predictive accuracy until it doesn't. Until we get diminishing returns. Okay. Okay, so we'll hit a peak, I guess, is what they're trying to say. The curse of dimensionality. It's weird. What the heck? So how do we guard against overfitting? By performing feature selection to include only variables that have predicted value or by performing dimension reduction, you'll learn about a number of specific dimension reduction algorithms in part 4. We'll deal with that later. But discriminant analysis performs dimension reduction as part of its procedure. That's kind of cool. Okay. Okay, so the analysis isn't one algorithm, but comes in many flavors. We're going to look at 2, linear discriminant analysis LDA and quadratic discriminant analysis QDA. In the next section, you'll learn how these algorithms work and how they differ. So for now, suffice it to say that LDA and QDA learn linear and curved decision boundaries between classes. Okay. So let's take a look at LDA first, and then we'll go to QDA. So imagine that we have 2 predictor variables, and we're trying to use to separate 2 classes. LDA aims to learn a new representation of the data that separates the centroid of each class. Whoa, what? Okay, so we have a bunch of dots in the middle of space. Each cluster of those dots has a centroid. And LDA aims to learn a new representation of the data that separates the centroid, while keeping the within-class variance as low as possible. Then LDA finds a line through the origin that, when the data is projected onto it, simultaneously does the following: maximizes the difference between the class centroids, minimizes the within-class variance along the line. Wow, this is kind of cool, but a little hard to think about. Here's our picture. So here we have 2 classes. There's a green class and a purple class. We've put it into 2-dimensional space. So LDA is finding a line so that we can project the centroid. We want to keep the variation, so So the within group variation, right, is the distance from like the smallest one to this biggest one on the line, right? That's what they're saying here with this purple underline, I guess. And for green, again, very similar, this S square. Okay, so maximize separation between class means, right? So we're taking the difference of the 2 means, squaring it probably to make it positive, minimize variation within each class. Minimize variation. Why are we summing it up to minimize the variation? So learning a discriminant function in 2 dimensions. LDA learns a new axis such that when the data is projected onto it, it maximizes the difference between class means while minimizing interclass variance. Okay, so I mean I guess that's where the formula comes from. Choose the line, the algorithm maximizes this expression over all possible axes. And now there's the sum of the variances of each class. The intuition behind this is that we want the means of the classes to be as separated as possible. Right, so we want this, wait, how are we doing this? We want the numerator to be as big as possible and the denominator to be as small as possible, right? We're trying to maximize this. Yeah, maximizes this expression. So maximizing this expression comes if we try to maximize the numerator and minimize the denominator. Got it. Okay. Right, so we want the difference of the means to be as separated or as big as possible. That's going to give us a large square difference. With the scatter or the variance within each class to be as small as possible, those are our two S squares. Okay. Why not simply find the line that maximizes the separation of the centroids? Because the line that best separates the centroids doesn't guarantee the best separation of the cases in the different classes. Okay, this is going to be important, I feel. This is illustrated in 5.4. So constructing a new axis that only maximizes this class centroid separation doesn't fully resolve the classes. What does that mean? What does that mean? Constructing a new axis that maximizes centroid separation while also minimizing variance results in better separation. Oh, better separation of the classes. I see. So this is what they mean by separation of the classes. It's not... okay, so the projection is designed to actually take these clusters and separate them, like actually physically separate them along this line. Right, and okay, so I think I understand why we're trying to do that. Because what happens is, if now we input a new item, like look at this. If we zoom in, they forgot to get rid of some of their like little pixels. I can see some of their pixels up here still. So I think the goal here is if we're inputting new data, and my new data looks a lot like stuff that's inside this cluster, we're going to be able to classify it as something inside that cluster if these groups are separated. But over here, because there's some ambiguity in these particular cases, if possible, it's better to choose this one, because then it's very clear how we want to predict that new piece of information coming in. Where here, I might be able to predict in some percentage of the cases, but I might not be as good as this other model, right? Like this one can predict pretty much in 100% of the cases almost, right? Or that predictability should be very high. Here it might be a little bit lower because of these weird overlapping cases. Okay, so I see now, I see what they mean by separating the classes now. That makes a lot more sense. Okay, so this new axis is called a discriminant function, and it is a linear combination of the original variables. For example, a discriminant function could be described by this equation. Sure. I don't know. So there's variances, and then there's weights. In this way, the discriminant... Oh, no, they're using df for discriminant function, and I usually use df for degrees of freedom. Is a linear combination of the variables var1, var2, var3. Oh, so those are variables, not variables. The combination is linear because we're simply adding together the contributions from each variable. Fine. And the values that each variable is multiplied by are called the discriminant function coefficients. Okay. And weights each variable by how much it contributes to class separation. Sure. So variables that contain little or no class separation information will have df coefficients closer to 0. So this 1.2 is pretty substantial. Yeah, even like the 0.85, even 0.5 to me would be probably substantial. But I guess if these start getting, closer to 0, then we just kind of start maybe to ignore them a bit more. I have not really come across principal component analysis before, so I'm just going to skip this. What if we have more than 2 classes? Discriminant analysis can handle classification problems with more than 2 classes, but how does it learn the best axis? Instead of trying to maximize the separation between class centroids, it maximizes the separation between each class centroid and the grand centroid of the data. Now, the grand centroid. You know what? I'm going to go out for Halloween as I'm going to go out as the grand centroid of the data set. What a great phrase. This is illustrated in figure 5.5, where we have 2 continuous measurements made on cases from 3 classes. The class centroids are shown with triangles, and the grand centroid is indicated by a cross. Okay, so initial input data. Sure, we have 3 clusters. We have the green triangle, yellow triangle, and purple triangle, which are the centroids of the respective classes. And then we have the grand centroid. Sure. Find discriminant function. So we should have 2 discriminant functions. In this case, because we have 3 classes. So we're going to project, we're basically projecting on each of these. Here, let's see if I can, new representation. See if I can talk myself through this before we read the... So yeah, so what I'm seeing is that all of these dots are getting, no, please draw. Hello, can I draw on? Yes, great. So all of these dots are getting projected in 2 different ways. They're getting projected onto DF1 and they're also getting projected onto DF2, right? Now, when we do that, it looks like they've also rotated, so when we do that projection and then use those axes as the new axes, is that how this is working? So DF1 and DF2 become new axes. So from a linear algebra perspective, that seems reasonable, right? We're going to project onto these lines. That's going to give us new ordered pairs that we can use to redistribute the data or kind of like rework with this data. So is that helpful? Yeah, I guess so, right? I guess the idea here is, I don't know, everything over here was already still pretty like, still pretty spread out, still fairly easy, I think, to work with. But I guess I could see instances where these projections, and then once you make that your new axes, I could see where you might be able to more clearly determine the classes, right? Or like separate these classes even more. Now here, I don't know, it doesn't look like we've really made much leeway on separation. But look at this. So I don't know, is it important that the grand centroid is now the centermost point of our axes? That seems interesting. That seems interesting. So they've taken DF1 and they said, okay, well maybe DF1 is running through here, maybe DF2 is running through here. So now all of the green data, yeah, ends up in this quadrant up here, right? And then all of our yellow data, it's kind of half and half, yeah. So I can kind of see like half of it here, but all over on the right-hand side. Yeah. And kind of same with purple. There's a little bit of overlap here with the new representation. Okay, so I wonder if they're going to say anything about the grand centroid being in the middle. That seems like it's probably important. It also makes those measurements easier too, right? If we're measuring from the center of the new axes, then it's easier to calculate distances. Okay, let's take a look at what they're saying here. So when there are more than two classes, LDA maximizes the distance between each class centroid triangles and the grand centroid cross while minimizing interclass variance. Once the first discriminant function is found, a second is constructed that is orthogonal. Oh, right. Right, so we find one of these, find the orthogonal. Okay, yeah. So we're using Gram-Schmidt process basically probably to find this new df function. That seems fine. Okay, the number of df's will be whichever is smaller. Yeah, we know that. So, I mean, if we're working in a higher dimensional space, then all these things are probably just going to be built orthogonal to each other. Makes a lot of sense. The data is then projected onto these new axes such that each case gets a discriminant score for each function. Huh? These discriminant scores, I think I understand what they're trying to say. So we're getting new components that we can use, or new ordered pairs that we can use to actually visualize this if we wanted to. All we're really doing, I guess, is a change of basis. In that particular example we looked at, it was just a change of basis. So what's the big deal? We've gone from having two predictor variables to having two predictor variables. In fact, you can see that all we've done is center and scale the data, rotate it around 0, right? So it's just change of basis in our example. When we only have two variables, the discriminant analysis cannot perform any dimension reduction because the number of df's is the smaller of the number of classes minus 1 and the number of variables, and we only have two variables. What about when we have more than two predictor variables? Okay, so 5.6 shows us something in higher dimension. So we have three classes, three variables, x, y, and z. So it's going to find df1. So now my question is, how does it find df2? Because it's going to... So it has some dotted lines here. So now I'm kind of curious about how it's going to find df2 here. Does it have to be orthogonal to a couple of different things? When there are more than two predictors, the cube represents the feature space with three predictor variables and three classes. Yeah. Discriminant function 1 is found, and then df2, which is orthogonal to df1, but there's a lot of... There's a lot of orthogonality that can happen here. If all I have to do is build something orthogonal, there's like an infinite number of ways to do that. What would make the most sense? I guess does df2 maybe... Oh, maybe there's another parameter here. So that once we find df1, how is this going to work? Like once we find df1, we find another orthogonal one, and then we start spinning it. So maybe we start spinning it until something happens, right? Like maybe that's how the algorithm works. And then there's a place along, like as we start spinning df2, we find a particular spot that maximizes the class separation. It's probably something weird like that. So next, LDA finds the second df, which is orthogonal to the first, which also tries to maximize separation while minimizing variance. Because we only have three classes, and the number of DFs is the smaller. Yeah, we stop at 2 DFs by taking the discriminant scores of each case in the data. We can plot our data into it. The first one does the best job at separating the classes, followed by the second. Okay, so I guess DF2 does something very similar. So DF1 is going to try to separate the classes as much as possible, and then DF2 is also, going to try. So again, there's an infinite number of orthogonal pieces or orthogonal DFs we could choose. So again, it must try to do a calculation to do that maximal separation piece. Okay. Blah, 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 blah. Okay, so that's pretty cool, but if instead of just 3 predictor variables, we had 1,000, LDA would still condense all this information into only 2 variables. That is actually pretty cool. Okay, so learning curves instead of straight lines. So LDA performs well if the data within each class is normally distributed and all the classes have similar covariance. So LDA assumes that for each class in the dataset, the predictor variables covary with each other the same amount. That might not always be true. Yeah, this often isn't the case, and the classes have different covariances. Right. In this situation, QDA tends to perform better because it doesn't make the assumption of covariances. Oh, interesting. Okay. But we still have to have normally distributed data. Okay, so QDA is probably more realistic than LDA is basically what they're saying. Instead of learning straight lines, QDA learns curved lines. Damn. Look at these little spinny spins. I don't even know what they're trying to say here. Examples of 2 classes which have equal covariance. The relationship between variable 1 and variable 2 is the same, and different covariance. What? And different covariances. Oh, equal covariances, different covariances, I see. I see. So they're saying that when there is unequal covariance, when we use the QDF process, we get bigger separation. It looks like they get, based on the picture, it looks like everything gets normalized in the sense that it's the same size. But I can see there's a bigger separation here in the QDF process than in the LDF process. In the example on the left figure, the 2 classes are normally distributed across both variables, have equal covariances. Equal because blah, 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 blah. This situation, LDA and QDA would find similar DFs. Although LDA is slightly less prone to overfitting than QDA is because it's less flexible. In the example on the right in the figure, the 2 classes are normally distributed, but their covariances are different. Yeah, in the situation, QDA will find a curved DF when the data is projected. That's cool too, like projecting onto a curved line. Oh gosh, look at this. This looks terrifying. Whichever method you've chosen, the functions have been constructed and you've reduced your high-dimensional data into a small number of discriminants. How do LDA and QDA use this information to classify new observations? Oh no, they use an extremely important and statistical theorem called Bayes' rule. No, I don't know Bayes' rule. Bayes' rule provides us with a way of answering the following question. Given the values of the predictor variables for any case in our data, what's the probability of that case belonging to class K? So K given X, right? So probability of being in class K given information about X. So given that we know X, what's the likelihood that we land in K? That's what this means. K represents membership in the class K, and X represents the values of the predictor variables, right? We would read this as the probability of belonging to class K given the data X, and that's equal to the probability of X given K, that's weird, times probability of K over probability of X. Don't be scared by that. I'm already scared. Too late. There are only 4 terms in the equation. I'm going to walk you through them. Great. You already know PKX. Yes. Yes, fine. PXK is the same thing but flipped. What's the probability of observing this data given the case belongs to class K? Put another way, if this case was in class K, what's the likelihood of it having the values of the predictor variables? Yep. PK is the prior probability and is simply the probability of any case belonging to class K. And PX is the probability of observing a case with exactly these predictor values. Yeah, that's fine. I don't know if any of this is super important. This feels like physics to me. Ugh, it's proportional to it. This looks like a weird infinity symbol. I don't like it. Okay, the prior probability, PK, is easy to work out. It's the proportion of the cases in the data set that already belong to class K. We would have that already when we go to input the data, but how do we calculate the likelihood? Yeah, the PXK. That's my question too. The likelihood is calculated by projecting the data onto its DFs and estimating its probability density. God damn. The probability density is the relative probability of observing a case with a particular combination of discriminant scores. I feel like I need to open up a stats book for this. Discriminant analysis assumes that the data is normally distributed, right? So it estimates the probability density by fitting a normal distribution to each class. Oh. The center of each normal distribution is the centroid, yep, and its standard deviation is 1 unit on the discriminant axis. It's illustrated in figure 5.8. Okay, what? Okay, one discriminant function. Probability density of point X belonging to this class. Where the center of each is the centroid of the class. Yeah, I feel like this is going to get tricky when you have more information. I'm not sure what they're trying to show here. Oh, I see. They're taking the two normally distributed things, making kind of like a 3-dimensional normal distribution and finding the centroid, right? The centroid is going to be that middlemost point. Okay. Triangles? They look like little ghosties. This is like Ghost K and Ghost J. So the procedure is estimated for each class, and the class that has the highest probability. I wish I could. Can we work through like? I want an example. Okay, it says, don't worry if you don't quite understand it, that's by design. Well, that's not a very good design. I kind of want to read a little bit more about this, if I can. Linear discriminant analysis. Computations for LDA. And because I'm going to end probably in 10 minutes, I don't want to write any code tonight. So I kind of want to read a little bit more about what the hell's going on here. Okay, let's go to page 101, because that seems to be where this is going to be. 101. Let's see if we can actually get some math in here today. Oh, this is page 428. That's way too far. How big is this book? Holy fuck. Wavelet smoothing? What? What does that mean? I want to smooth a wavelet. What did we say? 101? Here it is, linear discriminant analysis. I need to read anything up here? What? Suppose f sub kx is the class conditional density of x and class g equals k. and let pi of k be the prior probability class k. What? With all of the sums equaling 1. A simple application of Bayes' theorem. What? Gives us blah 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 blah. Okay, maybe I didn't want to see the mathematics, boys and girls. We see that, do we? I don't see anything. In terms of ability to classify, having blah is almost equivalent to having the quantity. Wait, having FK... F... Hey, Stuart. Is this hasty? Yeah, I think so. Yeah. I was working in Reese, but they didn't have like any calculation, so I'm like, I kind of just want to see like a little bit of the mathematics, and now I'm scared. Mostly because I haven't read like actual statistics in a long time. Okay, so what we want to look at is the linear and quadratic determinant analysis. So they use Gaussian densities because everything's normally distributed, right? More flexible mixtures of Gaussians allow for nonlinear decision boundaries, blah, 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 blah. Okay, naive Bayes. Suppose that we model each class density as multivariate Gaussian. I have no idea what that means. But let's just assume that's an assumption. So each f sub kx looks like this. This is just... I should probably know some of this. This looks kind of familiar. Like, this kind of looks like the distribution. What's this, though? Oh, this is the 1 over root pi or some shit. Yeah, if p is 1, then this is just 1 over root 2 pi or something like that. So that's just the coefficient that goes along with the Gaussian. So this is this must be in p dimensions then. This book is the Bible of statistical learning. You read it at least once every few years. God damn. Okay. I need to brush up my stat skills apparently, because I'm like, what is this? It's been a long time since I've had to look at stuff like this. So LDA arises in the special case when we assume that the classes have a common covariance matrix. Okay, so that's what Reese was saying. So that's an assumption for LDA that we need. So this is saying that, so this is the covariant matrix. I see. So for any k, they're all the same. So when comparing two classes, K and L, so the sub-Ks are our classes. Okay, so I'll get there eventually. It is sufficient to look at the log ratio. Okay, let's see if we can figure out where this is coming from. So they gave us this formula up here. And they want to take log of these, right? Wait, is it log of 1 divided by the other one? Right, so we should be able to break it up into the FK part and the summation part. So let's just see what they're doing here. So that's kind of what they're doing here, I think, right? They're breaking it up into the FK part, the pi part. Where does this go, though? Where does this thing go? It's very dense and requires very careful reading. Yeah. It requires very careful reading because they're like, we see that, or if we assume that. I'm like, what? and I have a little bit of not like a lack of statistical knowledge, but I just haven't read heavy-duty statistics in a long time. It's been like 20 years. So I might have to actually read this book from like the top of this book, so that I can get the lingo and the notation down a little bit more. So what is this? Okay, I'm gonna grab some stuff because I kind of want to understand a little bit more about what they're doing here. Okay, so this is what we have. This is each of our probabilities, right? So they're saying in terms of ability to classify, having this function is almost equivalent to having this quantity. So there's something important there. And I think Reese was saying that as well. But I want to know what some of these pieces are. So that I don't think we need to look at immediately. But let's take a look at this and see if I can make heads or tails of this business. Okay, so if we're gonna divide both of these things, then we should get the probability. Oops. There you go. Should get FKX pi k. Reading. Yeah, seriously. You might have to read sometimes.
Perfect calculations deliver perfect
Oh,
results.
thank you very much for the tier 1 subscription, Stuart. Much appreciated. Thank you very much. Thank you very much. Please enjoy your emote explosion. And if at any time you want to chime in because I'm being a complete noob, please let me know. G equals... Oh, wait. Wait. So this... L equals 1 to K. And then FL... X pi L. So that's the probability of G equals K, the probability of G equals K given X equals X. We need to divide that by G equals L given X equals X. So that would just flip everything. Oh, I see. So some of these things are going to cancel. Right, so this is going to cancel. Is this always L? Oh, that's part of this summation. Right. Okay, because the denominator is just the sum of all of the s squares, basically, right? Okay, so I think that denominator term is going to cancel. I see. That's how we're getting this, because we have the log of this. So if those cancel, that's going to let us break this up into log of, oops, FK, FL. Yeah, I see. Okay. And then we have pi k pi l. So that should work too, right? So we should be able to break this up because we have multiplication will turn into addition on the outside. Okay, cool. I can still do math. Okay, cool with that. Super happy with that. Now, each of these FKs, FK and FL, I guess we're gonna break them down. So now we have to use this. What's going on with the pi k pi l business? What are those? So I have a formula for this. Oh, I see. They have log of this minus some stuff plus some stuff. I see. Okay. So we're using logarithms here so that we can kind of get rid of the exponential here. So, or at least they're going to try to simplify it a little bit that way. Okay, so they still have this, which is this. So let's see if we can figure out where the rest of this business comes from. I don't like the new OneNote. The new OneNote kind of sucks. It's not as nice as the old OneNote. I used to be able to just like float around and it was very easy to like move around. It's not very easy to move around anymore. Okay, so let's put the log of pi k pi l out front. And then we have plus log. Oh, do all of these things cancel again too? They do. Okay, I got it. So basically we're going to have this. Each of our sigma k's is just sigma because we know that the covariance is the same. That's an assumption. Okay, so that assumption helps get rid of that coefficient. So we don't have to worry about that coefficient. So we're going to get this. Hi, Reese. How are you? Hello, buddy. Hi. Oh, hello. Hello. Oh, you're very big. Yes, you're very big. Oh, you're very good boys. Yes, you're very good. Okay. Lay down. Lay down. Yeah. Reese's here. Okay, I think once we... Oh, wait, is this the inverse of the covariance matrix? So this should still be inverted, right? But we need x minus mu k. And then we will divide that by this thing here, 2 pi p over 2 sigma 1/2. And then we have e negative half. So this is going to be x minus mu l transpose inverse of the covariance matrix, x minus mu l. So if my theory is correct, these two pieces we can cancel, right? Because everything is multiplied. And then that's going to allow us to, I guess, combine these exponentials. So we combine these exponentials by subtraction. So that means we're going to be left over with log pi k pi l plus, well, it's not going to be a plus, it's going to be minus 1/2 x minus mu k transpose. I don't know about this piece. We'll take a look in a second. And then we subtract this lower piece, but that's really an addition. So it's really plus 1/2 x minus mu l transpose inverse covariance x minus mu l. Okay. So is that what we're looking at? We're looking at something like that. Can we combine that? That's the other question. So it looks like they're trying to combine some stuff. So they have minus 1/2 mu k plus mu l. And then mu k minus mu l plus x transpose. What? What? I feel like I must be pretty damn close. But there must be some business. There must be some sneaky algebra business that I'm not getting here. Where do they get their mu k minus mu l? I guess I could distribute stuff. I don't particularly want to distribute stuff. But yeah, maybe there's a way to distribute this and factor it. What do they have here? What is this? I could factor this. I mean, that's similar in both. These are matrices though, right? So I have to be a little careful with how I factor stuff. I can factor that on the right. Right, mu k minus mu l. That would give me this. I don't know if that's helpful. Couldn't tell you. It must be like a statistical proof, right? There must be a way to move some stuff around here that I just am a little unsure of. I feel pretty good about what I did, though. I do feel pretty good about what we did. Okay, I'm gonna just leave that as maybe an open question. I might just throw that into the Discord server and ask if anyone can help. Help. Let's throw a new post in here. Help. What's the message here? Well, first let's get the picture in. So trying to understand these few lines from, this is, which book is this again? This is page 108, page 108. Hasty et al. From page 108 of Hasty et al. Trying to connect their final line with what I got. Any help is appreciated. Oh, that's true. Yeah, the mu k, mu l certainly would be... Yeah, would certainly be the difference between the centroids. That makes a lot of sense. Yeah, I think I've hit a wall with my statistical knowledge. I don't think I'm gonna really be able to think about it too much further. I'm gonna have to ask some knowledgeable people in the Discord server some questions. So it's kind of like a confusion matrix. Interesting. Okay. So multiplying that by the inverse. And again, I'm a little unsure of the properties of the covariance matrix and the inverse of the covariance matrix, so there might be some properties of that matrix that I'm a little unsure about that we can use here too. So it's probably something silly like that, right? It's just because I haven't really done a lot of multivariable stats, so I feel a little ill-equipped, I guess, to handle this one. All right, friends. It is about that time in our lives. I am going to wind down stream here for everybody. Sorry, just got a text from somebody. Oh yeah, HTF used that inverse covariance matrix all the time. Enters a lot. Oh, okay. So maybe I can go read about some stuff in chapter 2. That's a good. That might be what I'm missing. Okay, cool. So I'll take a look at their chapter 2. That's thank you very much for that information, Stuart, and I'll see if that helps out a little bit. Also, thank you very much for the tier 1 subscription. Much appreciated. We are doing quite a bit of work in mathematics. I'll throw the Discord invite in there. All of the materials we're using for machine learning are going to be in the machine learning section of the Discord. We have a lot of good stuff coming up this month. We do mathematics on Sundays. We'll be doing gaming on Wednesdays and Thursdays until we get to Halloween week, which will be doing a full week of Look Outside. So if you're in it for the mathematics, more about model selection. Oh, all good, all good. Chapter 3 that introduces the covariance matrix. Sweet. Okay, so maybe I'll make a little note for myself to check out Chapter 3. Before we come back next weekend. So I don't know exactly what the Sunday schedule is going to look like. I do want to learn a little bit of Python and do a little bit more machine learning. So right now I'm feeling pretty good about this particular chapter of machine learning. So I might come back to it next weekend, depending on what my time looks like, rather than doing Python work. But we'll see. We'll just kind of go Sunday by Sunday and see how things go. But until then, who is online? I got Darth on. I don't think any of our typical math streamers are online right now. I think most of our math streamers are offline. So we might just be winding down for the day, unless anyone has any specific recommendations of who we might be able to stream who's doing mathy type things. I'll pop up Chapter 3 right now. Chapter 3, linear, oh I see, so linear methods for regression. Alright, let's pop it off there, sweet, okay. Alright everyone, thanks for coming and hanging out for a little while. I'm going to go have some dinner. Probably have to get Reese out for a little bit of a walk here. We will be back on Wednesday evening, so doing some gaming Wednesday evening, and I think Dexy and I are going to be doing some Zelda on Thursday this week as well. So we'll catch you guys a little bit later. Thanks for hanging out, and we'll talk to you soon. Bye!